from Tansu Daylan, who is currently a postdoc at Princeton, but apparently, I guess, is soon going to be starting as faculty at Washington University in St. Louis. Tansu is going to be telling us all about the allesfitter code. So go ahead and take it away, Tansu.
Thanks, Eric. Hi, everyone. Well, first, thanks for the flexibility with the organization of this talk. Unfortunately, I couldn't deliver it on Tuesday because I've been pretty distressed by the earthquake in Turkey, but today I had the opportunity to talk to you. So I will be talking about allesfitter, and I have the privilege to be talking right after Jason because he already introduced the idea of global fitting, and he talked about one of the other major pipelines that does something very similar to allesfitter. There are certain nuances here and there. In addition to two others, Juliet and Exoplanet software, we basically share the market for being the widely publicly used Exoplanet analysis and modeling software, basically. So just before I start, this is a big collaboration that I have been doing with Max Günther, who is currently at ESA. And most of our collaboration was when we were back at MIT. Currently, I'm at Princeton, so this is pretty much past work, but we still continue to co-develop allesfitter and think about adding new features as new data sets come in. So I will be basically talking about allesfitter and how it fits within the landscape of these pipelines. So first of all, some motivation and ethos of allesfitter. Why allesfitter exists? Well, first of all, what allesfitter does is it helps us with indirect detection and characterization of exoplanets using time series data. And there are a couple of design philosophies we follow. First of all, we want to use statistics to our advantage so that we can test models robustly. And then we also aim for generality and flexibility. So we want the users to be able to try different models and essentially have this notion of global fitting. So you have all the data and all the models necessary and you dump them in and you basically do the most robust inference you can potentially, including many different submodels. And then we also aim for being able to benchmark. So we have multiple software that do something similar. And in order to support open science, we need to be reproducible and we need to have different pipelines agree and be able to benchmark on a particular data set. And finally, we want to also be accessible to undergraduates and early graduate students. So people, when they enter the field, the research field, they will not have the capability to write their own software pipelines. They may use allesfitter or software alike as a stepping stone. So they can maybe do their first project with allesfitter and eventually write their own pipelines. So this essentially lowers the barrier to enter a field. And I think it's one of the most important design philosophies of these software pipelines. And finally, one other thing I should mention is we think about archival research a lot, and automation is a big part of this. So in order to be able to automate these such analysis, we need well-established pipelines that one can just wrap and run on big data. And we also aim for automation. So I obviously cannot cover all aspects of allesfitter in a just 15-minute talk. So here is just a very crude list of, or the ingredient list of allesfitter. We basically wrap several important forward models. And there are others that are currently, I'm personally developing that will eventually be part of allesfitter. But as allesfitter stands right now, we are currently wrapping LC by Pierre Maxted, which is essentially our light curve and radial velocity global model. And then we are also using A-flare, which is a flare model from Jim. And finally, these all take care of like transit spots, Rossiter-McLaughlin, and phase modulations. These are all taken care of by LC, and Jim's pipeline essentially allows flares to be modeled. We also model limb darkening. We use the parameterization proposed by David back in 2013, David Kipping. And we treat both white noise as well as red noise. White noise is kind of easy. You rescale the noise in the data to adjust and marginalize over. And we also treat red noise, which is essentially it's a roof term that includes all features in the data that are not in your model. That's what we call red noise. And we use Gaussian processes to tackle that. And finally, for the inference part, so far I've talked about the forward model. In order to infer those models, we offer both MCMC capability and also nested sampling, the former via DFM's 2013 work MC, and the latter by Josh Spiegel's nested sampling dynasty. So I will just show couple of pretty pictures to engage people, but these will just be a couple of examples of how we make use of allesfitter. And then maybe in the questions, we can talk about other applications. This, what you're currently looking at is Pi Mensae, which was historically the very first test exoplanet discovered, which has some historical significance. But apart from that, it's a multiplanetary exoplanetary system. And Pi Mensae C was the first test discovery. Here you're looking at basically the Pi Mensae C folded transit light curve on the left. And then you're also looking at the radio velocity data at the center. And on the far right, you see the radio velocity data phase folded onto the period of Pi Mensae C, which is the new detection. And different data show the data from TESS and Anglo-Australian telescope. Basically, the idea here is that you have a global view. You can look at the transit data, the radio velocity data at the same time, and notice that these data have been background subtracted. So there is a separate background model which is jointly fit, and we subtract that background model to come up with the part of the data that should be immediately comparable to our forward model, which is a transit model, which includes transits, eclipses, phase curves, as I said, spots, Rossiter-McLaughlin effect, as well as flares. So this is basically, this is directly from our software paper, 2021, Günther and Daylan, 2021. The second plot here essentially shows us shows you the basic parameterization of a global fit. You have the radius ratio, you have the R sum divided by A, or rather the sum of the stellar radius and the planetary radius divided by A. We put a prior on this, trained on the density of the star. If you have questions, I can respond to that later. And then we have the other parameters like the ephemeridese parameters and the limb darkening. As I said, we use the Q parameterization for limb darkening, which is the transformed version of the linear and quadratic limb darkening parameters. We also use Bayesian evidence. As I said, robustness is an important ethos of allesfitter, so we want to be as statistically robust as possible. So on the top left, you see the posterior, the definition of posterior, which is essentially the probability of a particular chunk of parameter space as marginalized essentially over the parameter space at the center. So that's what you're seeing as the evidence. So that's the probability of data as marginalized over the parameter space for a particular model. And the Bayesian evidence is the evidence of one model divided by the other and also renormalized by the prior. Well, we usually give equal priors to different competing models. So that just means that we compare the Bayesian evidences for two different models. Here on the plot, you can see a couple of examples. You can compare linear versus quadratic limb darkening. You can compare eccentricity versus circularity, or you can compare different baselines. You can compare different numbers of flares or spots, or you can compare, for example, TTV versus no TTV. And then allesfitter also produces these generic tables, by the way. I mean, this is probably something that any advanced researcher can produce on themselves. But again, for accessibility purposes, we also make these available so that someone who enters the field right away can produce the tables and plots without losing too much time. And here is an example of TOI 216, which was a TTV detection from the test mission. And you can see that the transit timing variations are fitted separately for each transit. And you see both B and C here, C being the wider one. Again, I won't go into much detail here because respond to them later. Here you see the super periods of B and C separately, and this was essentially just a proof of principle that TTV fits using allesfitter actually works. Then we also do phase curves. Phase curves are important because you may want to study the atmospheric properties or the masses, which then reflect themselves as either ellipsoidal variations or Doppler beaming. So we have all of these components in the model by Pierre. Basically, LC includes all of these. We also, on top of LC, include sinusoidal and cosine components with certain offsets. So if you want to do, for example, phase curve studies with a particular offset, you can do so with allesfitter. By the way, the previous picture was of WASP 18b. Now, this one is from KOI 1003, and this is just a spotted star for illustration. Again, we can do spots. We can also do flares, as I mentioned. This is GJ 1243, and you can see a double flare and a single flare later on. And flares and spots are jointly fitted. For spotted flares, for spotted stars, typically they also flare at the same time. So you want a global model that models them at the same time. So a quick outlook before I finish. So allesfitter has so far been used widely for test data as well as QOPS, but we also want allesfitter to be applicable to future data sets. Coming up is basically the Roman mission, with which there will be a couple of community surveys as well as GI opportunities. And some of these will require high cadence data. For those high cadence data, especially the bulge survey, we can still do some transit science. And obviously, right after that, we will have Plato by the European Space Agency, and allesfitter will also be very much applicable to Plato data. But also barring any future data, allesfitter will continue to be used for archival tests, Kepler K2 data, QOPS data for sure, as well as future opportunities for transmission spectroscopy. So far, we haven't really used allesfitter for spectroscopy, but it can actually, within the same pipeline that's as published, we can actually use it for time series spectroscopy like HST, JWST, as well as futuristic data from Pandora SmallSat, as well as Ariel. So if you're interested in any of these applications, or if you want to build onto allesfitter or add modules, or basically just use allesfitter for any of these, or in general, if you're interested in astrostatistics, I will be starting a new group starting next fall at Washington University in St. Louis. So if you're interested, if you're a student or prospective postdoc, please do reach out for research opportunities. I'll just leave my this slide as my summary slide, and thank you for the opportunity to talk again. Sorry for the out of schedule talk, and I'm happy to take any questions.
No problem. Thank you very much, Tansu, for being able to get your talk in. That was really exciting. We have plenty of time for questions. If anyone has any, feel free to raise your hand. I guess I'll take my prerogative to ask you a question. You mentioned at the end about being able to fit to the transmission spectroscopy as well. I was just wondering, were there any particular challenges there? I know certainly, with all of the different instrument modes, are there any particular complications or challenges for getting it to run there?
Yeah. Yeah, so the main challenge with spectroscopy is that there can be many channels, as many as hundreds. And typically, when that's the case, you don't want to have parameters that are free all over different channels. Like, for example, with allesfitter, we do have the capability to have data from different wavelengths. For example, you could have, say, some ground-based telescope collecting photometric data at, say, 3 to 4 wide passbands. We have the capability to do that, but we do float individual parameters for all of those. But when you have JWST near spec data with 100 channels, for example, you don't want to float the separate GP parameters. Then you have to tie them together. So far, we do have the capability to tie them, but not in a very super elastic, flexible way. For example, we want to have flexible parameterization over wavelengths, and that does not yet exist. So that's something we are looking into. So there is some development opportunity over there.
Okay, thanks. Yeah, that certainly makes a lot of sense. I see, looked like there was a quick question in the WebEx chat. Thank you for the great talk, Tansu. How does allesfitter take into account the unique systematics of a telescope, say something like Cheops?
Right. So we basically have the Gaussian process as our main way to take into account red noise. And Gaussian process, when it comes to Gaussian process, obviously it's a family of curves that can span any arbitrary function. The important thing is to have some prior about the physics that goes into whatever is causing that red noise or unmodeled data features. And for ground-based telescopes, we typically use Matern 3.5 kernel, which is very jittery. And that's, I think, a good model for how the atmospheric scintillation actually manifests itself in photometric data. So we typically use Matern 3.5. You can go up to Matern 5.5 as well, but that becomes really jittery and probably overfits the data at really short timescales. So that is probably the nominal way to fit ground-based seeing limited data.
Okay, well, thank you very much. Well, let's all give a hand for Tansu again.